I'm David Swenson, and this is an OpenPathSampling mini tutorial. In today's tutorial, we're going to continue the work that we had done in the previous tutorial, working with SimStore and the new command line interface. The materials are available at SimStore and CLI within our mini tutorials repository. Just to remind you what we've been doing before, we had looked at this simple bistable double-well dimer model where we have a condensed version and an extended version of this dimer. It's in a bath of other particles. It's described by this simple double-well potential. We're going to look at doing TIS, transition interface sampling, with this model, and we're going to see how we can calculate rates using TIS. In our previous session on this, we showed you how to do the setup stage. So we're talking about splitting this problem into 3 stages. You set up your simulation, you run the simulation, and then you analyze the results. We've already done the setup using the SimStore way of doing the setup, our new storage subsystem. Now we're working on using the command line interface itself. So these are 2 separate things. You could have done the first part with NetCDF Plus, our old storage subsystem, but we did it with the new one. Now we're going to do a part using the command line interface. We're going to go from the snapshot that we had saved previously all the way to running transition interface sampling, replica exchange transition interface sampling, entirely through the command line with no Python. How are we going to do that? We're going to start out with that snapshot, and then we're going to get some initial trajectories that are not equilibrated into our correct ensemble by using high temperature molecular dynamics. We'll also need to then extend a little bit using the minus interface ensemble, extend with some direct molecular dynamics in the minus interface ensemble to get that ensemble ready. We can equilibrate that then, and then we'll be ready to actually run transition path sampling. Each of these things that's in the black box with the green text, that is a command that we will use from the command line interface. So here I am in a shell. OpenPathSampling is a command, just like a lot of other commands that you might know, that has a lot of subcommands. The way Git has subcommands, the way Conda has subcommands. So we can look at what those possible commands are by looking at the help by -h, and we have some simulation commands that we see that are in the current version of it, as well as some miscellaneous commands. Those miscellaneous commands we're going to use to help us work with OpenPathSampling output files. We could look at any one of these in detail. Let's say I wanted to look at the path sampling command in more detail. I could do OpenPathSampling path sampling to look at that command, -h to get the help for that, and it'll tell me what I need to do to put in there. Now I want to look at this OpenPathSampling contents command, and we're going to look at the file that we created before, the setup.db. And when we do that, we'll see what the contents of that file are. We see that we have a CV named R. We have volumes called condensed and extended. Those are our state definitions. And there are some others that are apparently used along the way. Those will be our interfaces and things that are helpers for our interfaces. We have 2 different engines. Remember, we made a regular engine and a high temperature engine so that we could run the molecular dynamics at high temperature. We have a network named TIS. We have a move scheme called Retus scheme. We have a couple of tags. You remember we saved some things that we were going to reuse later, this tau and this sigma nm. We don't have any trajectories, we just have one snapshot, so we're going to be able to start from there. The way that we will get initial conditions is by using the visitAll command. So visitAll runs dynamics until all of the states that you list on the command line have been visited. And this is a great way of ensuring that you have trajectories that will satisfy initial conditions, for example, for multiple state TIS. It'll also work for regular TIS, as we're doing here, or for TPS if you're doing a 2-state TPS. So to do that, we need to specify that we're going to do the visitAll command. We're going to take things out of our setup.db, that's our file that we're getting our information out of. Our output, I'm going to call this longtraj.db. Now we need to define our states. So we have one state called condensed, another state called extended. We need to define which engine we're going to use. This is why we have our high temperature engine, so we can accelerate these transitions and get initial trajectories, which will then equilibrate into something physical. Now we don't actually have to provide the initial frame because there's only one snapshot in setup.db, so OPS is smart enough to figure out that's what you want to use. And when we run it, it'll take a second to get started, and it helps if I actually spell the engine correctly. And now we should see very soon that it's going to start running. It's already found the extended state, as it says there, and it's looking for our condensed state. There it is. It found it, it's saving the trajectory, and we will be able to move on to the next stage. So now what we need to do is transfer that information back over to the right place. So if we look at OpenPathSampling contents of visit all, and sorry, we called that longtrash.db. So these are the contents of our file. What we'll see is we have the engines. We have both of the engines because the initial snapshot actually was created with the original engine or associated with the original engine. We have a tag called final conditions. That is what we created. That's the result of our simulation. We have a bunch of snapshots that made up one trajectory. So what we need to do now is transfer that trajectory, which is tagged as final conditions, back to our setup file. So we'll use the append command. And so we'll take it from, we called this longtrash.db, and we're appending to -a append to setup.db. And we're going to take the tag that was called final conditions, and we're going to save it under a new name. I'm just going to call that longtrash. So that'll take just a second to copy that information over. And once we do, we'll take a look inside the contents of setup.db. Let me clear the screen. And what do we have? We have now a new tag, longtrash, as well as all those snapshots in that one trajectory. Now the thing is, we could try to equilibrate now using setup.db. And this would be, this is all we would need to do that in principle. Oh, sorry, I need to give it an output file. So let's call it equil.db for the output file. It can interpret, OPS can guess a lot of what we need inside. What we're going to see though is there's a problem here. We're missing this condensed MIS minus ensemble. So what's going on here? Why is this working the way it does? Well, here's what our initial trajectory looks like that we did for our long trajectory. It started out in the extended state, remember, and so it wanders around there for a while before it finally finds the condensed state. But our minus trajectory needs to look something like this. It needs to start in the condensed state, leave the blue interface, the innermost interface, and wiggle around for a while in the state before again leaving the interface for a little excursion before coming back. One thing you'll notice here, the minus interface can be very long. That's one of the reasons we tend to do it less frequently than we do other moves. But how do we get this from that previous trajectory? This trajectory does not include anything that looks like the minus interface for the condensed state at least. But you can imagine that if we just sort of extended from the end of that trajectory, we might be able to get something that does that. And so that's exactly what we are going to do. We'll use the last frame of the long trajectory to create this. We'll use the OpenPathSampling MD command. What this will allow us to do is to run MD until we satisfy some ensemble, or give a fixed number of steps. But in this case, we want to satisfy some ensemble. And so what we want to do this, we'll do OpenPathSampling MD. We're coming from setup, is where we're getting our information. The ensemble that we want to run was called, and we have to put this in quotes because there are spaces, condensed MIS minus. And we're going to run this using our normal engine, not the high temperature engine, but the normal engine. And we're going to run from the frame that is the last one that was saved, which I know is the one that we need to actually start from. And I'm going to save this into -trash.db. So now we'll let that run until the ensemble is satisfied. That did not take very long. So what I'll do now is, again, I will transfer that. I will append from -trash.db to setup.db. And again, this is the thing that was tagged previously. It's always called final conditions. And we will save that as -trash. And so that won't take too long. So now we have everything we need in order to equilibrate. So let's do OpenPathSampling equilibrate. We'll take it from setup.db. I'll call this equil.db for the output. And if I just run that, what happens now? A lot of things it can figure out, but it tells us that we can't guess which item to use from sample sets. It doesn't know what the initial conditions should be. And we can see that if we do OpenPathSampling equilibrate-h, we can give -t or --initcons for initial conditions. We can give that more than once. And so what we're going to do is we're going to give those tags that we saved as for that. So it's OpenPathSampling equilibrate. Take it from setup.db, we'll save it to equil.db. We need initial conditions are long trash, and again we'll do initial conditions for minus trash. And it can figure out what the move scheme to use is. Always helps if I spell things correctly. So now it is looking for these samples, and it finds that we have nothing missing, nothing extra. So now it needs to just run until it decorrelates. Now this equilibration is kind of a minimal decorrelation. It just means that all frames, we're doing one-way shooting, so it's until all frames from the initial paths are no longer in the trajectories at all. This is not really necessarily fully decorrelated, but it's a minimal start, and it takes us just a little while to get it done. Once that's done, we will again take the stuff that is in there. So if we look at contents of equil.db, once again, we're going to have a saved tag of final conditions. It's actually the same thing as a saved tag equilibrated. So what I'm going to do is I'm going to append that going from our equil.db, appending to setup.db, and I'm going to take the tag that is called final conditions. Equilibrated is actually the same thing. I'm going to save it as initial conditions. And this is a special name that if you have a sample set or trajectory tagged with initial conditions, OPS will try to start your simulation with that. So we transfer it over. And now, once that's done, we are ready to actually start our path sampling. So if I look at our setup.db, by looking at our contents, we'll see that there's a lot more in it now than there had been before. In addition to all the volumes and things we saw before, now we've got these new tags of initial conditions and things like that. And so we are now ready to actually just run our path sampling. So let's do that. OpenPathSampling, pathsampling-h. Let's look at the help for it. So we need an output file. We'll be able to figure out the scheme because there's only one move scheme in our contents. We'll be able to figure out the initial conditions because the initial conditions have the special name initial conditions. So we just have to say that we want to do path sampling, take it from the setup.db, let's output it into tis.db, and then let's run for 5,000 steps. It'll load up the right information, it'll get the simulation started, and now we are running. So in today's tutorial, we've taken you from a snapshot that you'd saved before all the way up to running replica exchange transition interface sampling without a single line of Python. It's all been done with the OpenPathSampling Command Line Interface. I hope you've enjoyed it, and we hope that you'll join us in the next part of this three-part session where we're going to analyze these results from the simulation that we're running right now.